Welcome to summer assignment tutorial number 3 on temperature. And first off, I want to give a brief definition of really what temperature is. If I asked you what a definition of temperature was in class or right now, could you really describe what it is? A lot of people say how hot or cold something is, and it really is not an accurate description of what temperature is. A better definition of temperature is the average kinetic energy of particles in a substance. The average kinetic energy of the particles in a substance, meaning the atoms or the molecules that the substance is made up of. So what do we mean by kinetic energy? Kinetic energy is simply the energy of motion. So it's a measure really of how much motion particles have. And in class, we'll take a look at some models of solids, liquids, and gases at various temperatures, and you'll be able to actually visually see how their kinetic energy changes and how that's related to temperature. But for now, just keep in mind that temperature is a measure of the average kinetic energy of particles. There's 3 main temperature scales: Kelvin, Celsius, and Fahrenheit. Here in the United States, we always use Fahrenheit, or pretty often. You hear that in our weather forecasts and so forth. We are really just about the only country now in the world that is not using the metric system regularly. So we're stuck back with Fahrenheit. But if you hop over the border to Canada, you will see your weather reports given in Celsius instead of Fahrenheit. So let's take a look at the differences in these temperature scales. And Kelvin, by the way, is used a lot in science. We use it in chemistry, especially when we're dealing with gases. Okay? And what we're going to do is establish some baselines to compare these temperature scales. And the first baseline that I want to establish here is the baseline called absolute zero. And what does absolute zero mean? It means this is the temperature where there's actually no particle motion. Boy, sorry, that's a little small. No particle motion. If there's no particle motion, that means if we go up to here, there's no kinetic energy. So absolute zero on the Kelvin scale is 0 Kelvin. 0 Kelvin. And we don't use degrees on the Kelvin scale. We just say 0 Kelvin. Whereas on the Celsius scale, absolute zero, or the temperature at which there is no particle motion, is minus 273 degrees Celsius. Or we could be really, really particular and say minus 273.15 degrees Celsius. Okay, so let's compare just Kelvin and Celsius for right now. Okay, so that is absolute zero, temperature of no particle motion. Now let's look at another baseline. And this other baseline here would be freezing water. Okay, the freezing temperature of water, the temperature at which water turns into a solid. So what temperatures are those? In Kelvin, the freezing point of water is 273 Kelvin. And in Celsius, it is 0 degrees Celsius. Okay? And we can hop over to the Fahrenheit scale for now, because now we're in familiar territory. The freezing temperature of water in Fahrenheit is 32 degrees Fahrenheit. And we'll go and look at another common benchmark, and that is the boiling point of water. So use a black line here, but I'll use a red label. So when we have boiling water, so water now is being transformed into from a liquid to a gas. The boiling temperature of water in Kelvin is 373 Kelvin. And the boiling temperature of water in Celsius is 100 degrees Celsius. And the boiling temperature of water in Fahrenheit if you do a lot of cooking, you should remember it's 212 degrees Fahrenheit. So let's now compare these scales. I'm going to draw some dotted lines here because they are connecting the same events. Freezing water here is being connected with a dotted line. Boiling water here is being connected with a dotted line. And absolute zero is being connected with a dotted line. And I got to go back and figure out what it is here in Fahrenheit. Oh, actually, we can do that then. Okay. But if we look at some common observations here, the temperature difference between freezing water and boiling water on the Kelvin scale and freezing water and boiling water on the Celsius scale is 100 degrees. So in other words, we have the same temperature intervals here. This is 100 degrees. Okay, and this is 100 degrees. It's the same temperature interval. So really what that means here is that in terms of magnitude, 1 Kelvin equals 1 degree Celsius. In terms of magnitude, in other words, in terms of, we can make 100 little lines in between here and here, and they are the same magnitude. They're equal to the same amount. So 1 degree on the Kelvin scale is equal to 1 degree on the Celsius scale. However, if we look over here, the difference between 32 degrees Fahrenheit and 212 degrees Fahrenheit isn't 100, but rather it's 180. So they are not the same at all. So what does that tell us? It tells us that converting from Kelvin to Celsius and Celsius to Kelvin is pretty easy. I mean, really easy. Whereas making the conversions to Fahrenheit involve a little bit more math, because you don't have 1 degree of Celsius is not equal to 1 degree of Fahrenheit, and 1 degree of Kelvin is not equal to 1 degree of Fahrenheit either. Okay? So those are the basics of these temperature scales. So remember that absolute zero means no particle motion, and that is 0 Kelvin. That's equal to minus 273 Celsius. Okay, and then the freezing point of water is 273 Kelvin, but 0 degrees Celsius. The boiling point of water is 373 Kelvin, or 100 degrees Celsius. So when we look at just these two temperature scales, okay, we're looking at these two, you should really be able to come up with the conversion factors. So how do we go from, for instance, Celsius to Kelvin? If we go from Celsius to Kelvin, if we're looking at absolute zero, it's from minus 273 to 0. So we're adding 273. If we're at the boiling point, we're going from 0 to 273. We're adding 273. We're going, the freezing point. We go to the boiling point. We go from 100 to 373. Again, we're adding 273. So if we're going from degrees Celsius to Kelvin, what do? We add 273. Okay, or we could say 273.15 if you really want to be picky about it. If we want to go from Kelvin to Celsius, we're going backwards now, Kelvin to Celsius. At absolute zero, we're going from 0 to minus 273. We're at the freezing point, we're going from 273 down to 0. And if we're going at the boiling point, 373 to 100. So if we're going from Kelvin to degrees Celsius, this time we're subtracting 273. Very easy. You can almost do that in your head. Okay. However, if we're going from Celsius to Fahrenheit, that's a little weirder. Okay. So if we're going from Celsius to Fahrenheit or Fahrenheit to Celsius, if we want degrees Fahrenheit, this is going to be equal to 9/5. We got to use a little algebra, times our temperature in Celsius plus 32. And if we want to go from Fahrenheit to Celsius, we want degrees Celsius, that's 5/9. This time times the quantity, times our temperature in Fahrenheit minus 32. That's a quantity here. It's a little bit different from this guy. All right. The way that I remember this is, you remember 9/5 and 5/9 is that if I want Fahrenheit, the numbers in Fahrenheit are bigger than the numbers in Celsius. Okay, so my fraction is 9/5. Okay, if I want Celsius, my numbers in Celsius are smaller than Fahrenheit, so my fraction is 5/9 because that's a smaller fraction than 9/5. That's how I remember it. Okay, and since I want to go bigger to get to Fahrenheit, I'm adding 32, and if I go smaller to Celsius, I'm subtracting 32. The only difference is I have to remember here that for Celsius, I'm using this quantity here. Okay, so we can use that math here and we can figure out what absolute zero is in Fahrenheit. Okay, so how do we do that? Well, we know that absolute zero in Celsius is minus 273. So I want to go to Fahrenheit. So absolute zero in Fahrenheit is going to be, I'm using the equation, I'll just rewrite this. Degrees Fahrenheit is 9/5 times my temperature in Celsius plus 32. So I have 9/5 times minus 273 plus 32. So what I can do now is, to do this, 9/5 is equal to about 1.8. So I'm taking minus 1.8 times minus 273 plus 32, and I can bring up my calculator. Okay, and 1.8 times minus 273 is equal to 491.4. I think that's what it said. Let me pull this guy up again. Yes, and I'm going to add 32. So that plus 32 is equal to 523.4, but this should be negative because 1.8 times minus 273 is negative 491.4. I think I made a mistake. Hold on. Let's go back and clear that. So I have minus 491.4 plus 32. I should recheck my math. So minus 459.4. Yeah, that sounds a little bit better. Degrees Fahrenheit. Sorry about that math error. Okay, if you look at the time, it's 8:32 p.m., the evening of the first day of school, and I'm a little tired. So if we look at absolute zero in Fahrenheit, it's about minus 460 degrees Fahrenheit. And hopefully that I've done that correct. But this is just an application now and going from Celsius to Fahrenheit. And it's kind of a pain in the butt. I mean, I'm just going to be honest about it. And you should be aware of knowing how to do it. However, it isn't something that's really absolutely necessary to do in chemistry. Because basically, in science, we work in the metric system. So we're working in Celsius for the most part. And sometimes we're already in Kelvin, but if we're in Celsius, it's super easy to go to Kelvin and vice versa. These are really the two temperature scales we're working with in chemistry. And when we work with gases, all right, we're going to work in Kelvin almost all the time. And why is that? It's really because the absolute zero, or is because when we have zero particle motion, at absolute zero, that's equal to 0 Kelvin. They are directly proportionate to each other. In other words, average kinetic energy and the Kelvin scale are directly proportionate to each other. It's a good measure of kinetic energy, that temperature scale.